Hello, everybody. Welcome back to my YouTube channel. I'm glad you're here. This is the only review you'll need for the Discrete FRQs this exam. So what I'm going to do is I'm just going to list out all four of the types of FRQs that we might see and then the types per section. Okay, so the first one that we'll probably deal with is a general proof. And I wouldn't be surprised if it's going to be proving a bunch of things with each different method, kind of similar to what we already saw this year. General proof, there's 5 that we know. There's the direct proof. What else? There's the contraposition proof. There's the contradiction proof. There's a proof by cases. And then proof by exhaustion. That's about it for general proof. For big O, I kind of worked on this a little bit before, and it took me a while to type this part out, and so I'm just going to copy and paste it. Those are the 3 types that we might see. You know, the upper bound, the big theta. I don't know what the lower bound is called, but that's the lower bound. Yeah, so those are the 3. I would expect a big theta. Let's see. I should probably go over the order. I'll format it like this. It'll be easier. So the lowest is O1. So O1's always smaller than everything that will keep going. Next one would be O log n. Next one should be O of n. Next one should be O log n. Wait, no, n log n. This should be n squared. This should be, just to show that exponents always raise it, O n cubed. I think it should be 2 raised to the n, and then the last one should be n factorial. It should be the big O. Okay. Then we have the mathematical induction, and that's when we have this one will have both weak and then we'll have strong. And then the last part should just be what's the last one? Oh, just structural induction. But it's even easier this time because they gave us the type of induction. Oh my god. Recursive. Oops. Definition. So those are even easier. Okay. That is all the FRQs. We could quickly go over what each type is. So the direct proof is when you declare. So direct proof is when we have like a P implies Q. So you just declare P to be true. And this could just be like, if n is odd, then n equals 2k plus 1, something like that. Contraposition, again, in the PQ form, that is when you just you flip a negate, and so now we have not Q implies not P, and then declare not Q to be true. Contradiction in that form, it could be in that or just like a proposition. Contradiction is just you declare it to not be true, and so just say you declare. So if we're in this form, then Q is not true. Show why it's impossible. If it's just P, then negate and show why it's impossible. Okay, proof by cases. This one's kind of a lot of work when there's set amount of numbers you can use. That's how I think of it. Proof by cases is like, I guess we should say it's like infinite. When we're trying to do something infinite, and it's like proving something with the only possible values that it could have. Then proof by exhaustion is just bounded. So it's like if it's saying like this is true on interval 1 through 4, it's super easy. Just use proof by exhaustion and go through 1 through 4. So set amount of possible numbers. Big O, big theta. This is just, I don't really know how to go over these. It's really just finding, they're going to give you f of x, they're going to give you g of x, and the main goal is to find a c and a k that makes either of these statements true, knowing all these rules. And that should be it. I like to use limits to prove mine, and they seem to be okay with that. I guess like tools, you could use limits to show growth. And then you could also just remember log rules. I think that should be good to go. Mathematical induction, there's weak. This is just when we have, remember that we want to show 4 steps. We want to have our Pn. So what is it that we're trying to prove? B is our basis. Show that the basis of Pn is true. There's a few more steps. The inductive hypothesis, which is just that assume now pk is true given the basis. The inductive step is we must show how if pk is true, then pk plus 1 is true. And this is a lot. Hopefully it's just a simple inequality. If it's an inequality, you just plug in the k plus 1 when needed. It should be good to go. That should be it. And then I guess a conclusion. Oops. And strong is really similar. And in the way that we have our Pn, we have our basis. It's true, but now we use multiple bases. Strong is, I think typically when we see strong, it's like multiple bases that we could use. Your inductive hypothesis is now going to be a little different, where now we assume something like, assume pj is true, given is true on the interval of your lower bound is less bound j k, where k your upper bound. And so what this means is your lower bound is what you find in your basis. So what's the lowest thing you can show? And then k is greater than or equal to your upper bound is whatever you find also in your basis, the last thing you show in your basis. And then now your IS is really similar still, where we're trying to prove we must show pk leads to pk plus 1 is true. And this is done by showing how we get to k plus 1 using our basis. And this is kind of weird. Just basically you're going to subtract your j with a number, and then you're going to add whatever you need to get to k plus 1. And you're going to subtract using a legal move in your basis. And then your structural induction is really similar, almost. I want to say it's just, honestly, I would say, we could copy this over. What is it that we're trying to prove? Or sometimes, since we already know this is a recursive set, we could just say the set for the pairs that do this are in the set. Basis, show the basis of Pn is true. Same thing. So whatever definition calls for, that's the basis. Inductive hypothesis is assume we have an arbitrary pair. So now you want to assume we have an arbitrary pair that also meets this requirement is true. Is true, yeah. And then your inductive step is just, we want to show how every step following our basis will still meet the requirement. And the way I do this is just case by case, aiming the definition in the question. Okay. That should be all the FRQs. Thanks.